Changing magnetic flux is often said to induce an EMF in a circuit loop. Let's see what that means. Uh, so suppose we've got a region here of magnetic field, uniform magnetic field pointing out of the page, and suppose it's getting stronger with time. And then let's have a rectangular loop of wire here made of some material, some ohmic material that has resistivity rho. And if we take a little segment of wire, we see that it has a circular cross-section area that we'll call A, like this, a sort of script A. Then let's say the area of this rectangle, like this length times this width, let's call that capital A. And I just want to distinguish those two different areas. The cross-sectional area of our little wire segment, that very small area, as opposed to this length times width, this big area bounded by our wire. Okay, to change things up a bit from the previous examples, I would like to imagine that we have a path around this rectangular loop that goes clockwise instead of counterclockwise. So I'm going to define DS's as going clockwise around that loop. And then by right-hand rule, to get Lenz's law to work out and to get Faraday's law to work out, if my DS's are going clockwise around, then my dA for our surface area vector should point with my thumb into the page. So our dA's for these little patches of surface area point into the page opposite the B field, which is pointing out. So we'd be looking at the quote-unquote backside of this open surface bounded by the wire loop. All right, so let's apply Faraday's law to this loop here. Faraday's law stated like so. And then add in Ohm's law, knowing that the induced electric field that we're expecting a clockwise field. Let's run through that argument again. If B is getting stronger with time, then we have a magnetic flux that's pointing out of the page and getting bigger. So we need to add flux into the page to counter that. That's our Lenz's law principle, that inertia of our system, the electromagnetic inertia. So we need to add B flux inward. We'll get that if we have a current running clockwise around this loop, adding magnetic flux inward. Okay, so to get a current running clockwise, an induced current running clockwise, we must have an induced electric field circulating generally clockwise to drive that current. So our induced electric field, if this material is ohmic, can be related to the induced current density J. So our current density J must also be pointing at all points on our wire clockwise in order to generate the needed magnetic field into the page to oppose our increasing magnetic flux out of the page. Okay, so our E field, our induced E and J are kind of pointing in this clockwise direction. Let's sub this into Faraday's law right here. Put rho J in for E. So doing that, rho times J induced, and let's look at this dot product here. J and ds are in the same direction. That's by my choice. I picked the ds's to be clockwise this time. So J dot ds just gives us a cosine of 0. So this would be rho times the magnitude of the induced current density times ds. And if our material is uniform and we have a steady state induced current running around here, then that rho and that J should be the same at all points in the wire. If our cross-sectional area is the same and I is the same, then rho and J are the same. So we can pull rho and J out of this integral. Also represent J as the current induced divided by the cross-sectional area of our wire. That's script A, this area, not that area, but this area. And then we're left with adding up all the ds's all the way around our rectangular loop. So just repackaging these terms here, I have the induced current times this, the rho, times this will be end up being the total length of wire here. Once we add up all the ds's, we'll get the perimeter of that rectangle, the total length of wire. divided by the cross-sectional area of the wire itself, which we recognize as representing the total resistance, capital R, of this entire length of wire. In other words, we're showing here that the left-hand side of Faraday's law, as applied to this wire loop, is exactly equal to IR, the current running, the induced current running through that wire times the resistance of the total resistance of that wire. So the left-hand side of Faraday's law can, in this case, be replaced with IR, set that equal to the right-hand side of Faraday's law, and this looks now like I times R. We know that to be a voltage, a potential difference. It looks like this term here, the opposite of the rate of change of magnetic flux, looks like it's behaving like an EMF. It looks like our changing magnetic flux is driving current around that loop. So in fact, we call this the induced EMF. This right here, this rate of change of magnetic flux is behaving like a battery. This changing B field is behaving like a battery, driving this induced current clockwise around here. So we could think of this changing magnetic field as actually behaving like as if there was a battery there, and the total resistance in the wire could be added up and represented as some resistor over here. And even though there's no actual battery present here, the changing magnetic field makes this rectangular wire behave just like this. Now, if there's current flowing here and there's resistance, we know because of that resistivity, some energy is going to be dissipated as heat. So there's definitely energy transfers going on here. This wire will be heating up as the B field is changing. So where's that thermal energy coming from? It must be being delivered to our wire by whatever is changing this B field in the first place. So somewhere off the screen, somewhere there's some system controlling this B field, making the B field get stronger. That system is, through electromagnetic interactions, transferring energy into the wire, driving the currents, and then dissipating some of that energy as heat here. Okay, so there we have it. We see that this term here can often be thought of as representing an induced EMF due to a changing magnetic flux. And so, let's see, maybe one note here before we get to the big finale. I changed the direction of the DS and A in this example, so I want to verify how our signs work out in this case. Let's go back up here to our picture. If the DS's are clockwise and our DA's are then inward by right-hand rule, then the magnetic flux through a rectangular loop, given by this expression, well, our B and DA are anti-parallel to each other by my choice of DA and DS. So that gives us a minus sign right there. So our magnetic flux is negative in this case. Since the B field is outward, and I'm defining inward to be the positive direction. I'm defining it that way. So we've got a negative magnetic flux. And so our induced EMF equal to the opposite of the time derivative of that flux is the opposite of the time derivative of minus B times A. This A is the length times width, the actual area of our rectangle. So that minus and minus cancel each other out. So our induced EMF is just equal to plus A dB dt. We said our B field was getting stronger with time, so dB dt is positive, A is obviously positive, and our induced EMF, which came from this, is also obviously positive. So by thinking carefully about those signs and the directions of the DS's and the DA's and the B's versus the DA's, we've gotten all the signs to work out. So positive on the left-hand side equals positive on the right-hand side. Okay, that's kind of our Lenz's law sign issue, if we're very careful about it. And no reason not to be. So then, I guess, here at last, we have the Faraday's law of induction in its final form, often written like this. We say that an induced EMF in a circuit loop is related to the induced electric field circulating around that loop, driving an induced current around that loop, which is ultimately caused by our changing magnetic flux through the loop. And explicitly, that's minus d dt of this open surface integral. This is our magnetic flux here by definition of B dot dA over the open surface bounded by our wire loop.